Hello. Today's topic is about Taylor series expansions and the theoretical analysis of truncation errors. Taylor series expansions seem to be the only tool, or I believe it's just the only tool we can use to do theoretical analysis of truncation errors. So from this module arm, or this chapter arm, we will see the applications of Taylor series expansions a lot and often, of course. Okay, first review. Taylor series. Okay, we studied Taylor series or infinite series sequences in calculus 2. Okay, there we started such a theorem, Taylor series. Okay, if f of x has a power series expansion at a point A, then f of x can be expressed as such an infinite series. Okay, well, here. This means it's, okay, a minus r, a plus r. Okay. And this interval is said what? Do you still remember the concept? The interval of convergence. And this r is the radius of convergence of this infinite series. Okay, so if this one we expanded this function infinite series in summation notation, if we expand it, it's in this way. Okay, now given that we just expand to this n plus 1th term, we stop here because this one is an infinite series, so there are infinitely many other terms from the yes. Now we use r sub m of x to denote it. Okay, it's the remainder of this series. When we use this part, if we denote it like p sub n of x, it's the Taylor polynomial of degree n. Okay, now when we use p sub m to approximate f of x, this is the remainder, and we have a theorem or inequality is Taylor's inequality. Okay, it's to estimate the magnitude of this Rm, the remainder. Okay, given that this is this, okay, the next here, that's this term, the next term. Okay, given that the derivative is finite one. Okay, so over the interval of which one convergence, and we have this. This is the estimation of what of the actually this part. If we use the fourth term, n plus 1 terms to approximate f of x, and this part is called the truncation error. That inequality actually is used to give us theoretically an estimation of what the truncation error. Okay, so given that is this, okay, this is true, it's this. That's a minus h, a plus h. Okay, it's this open interval. And we assume h is small, as small as we please. Also, it just simply we say, hey, h goes to 0. In that case, this, and you must have watched one video recorded for last also module, or the recorded for I believe it's for last module. Okay, and then we have a big old notation. And what's this? This is a witness of such a relation, this function and this function. Okay, so therefore we'll say this guy is this. Okay, it's big O of this. H raised to the power n plus 1. Okay, that's the review of what Taylor series expansion and Taylor's inequality. Okay, next we'll play games now. In this talk, we will try to see how we'll see Taylor series expansions in action. Okay. Before we see how to apply, how to use Taylor series expansions to do something. Now, especially in this talk, we try to use Taylor series expansions to derive the finite difference formulas for various derivatives. Okay. Now before that we'll prepare for something. Okay, and make it ready. Now that's the very theorem we just reviewed, and now we just play symbolic game. First, we change each x to a capital X in the formula, capital X, and then capital X, we change a to little x. That's fine, right? So we have such a formula. Okay, we have such a formula. This is change a to little x. So we have this formula. That's just symbolic game. Okay, now we let capital X be little x plus h. And therefore, capital X minus little x is h, right? Okay, now we substitute these two into that formula, we'll arrive at this. Okay. And this part is h, so we will have this simply h. That's it. And we expand it, it's this. We get this formula. Okay, f of x plus h is given by this. And one more step. Now, based on this formula, we will do this. We will change x to x sub I. What's that? Okay, that's this. We assume over a given interval, we will have, say, hey, from A to B, say for example, okay, A to B. This is x0, this is x1, x2, x3, and so on. And all the data, those points, x1, x2, x3, x0, they're data points. They are called nodes. Nodes or data points or points. Okay, we assume the points are equally spaced. Okay, so now we change this x to this x sub I, x1, x2, x3, x sub I. Okay, x sub I, or xi anyway. So you change all x to xi, s, xi, xi, xi. Yes, just change it. We get this formula. Yes, now we are almost ready to do things. Okay, you don't have to memorize this formula. Okay, now, yes, with this formula we just derived. Okay, in this formula, xi is constant. Therefore, only h, as you can see, which thing is a variable in this expression? It's h. And when we take a limit as h goes to 0, say, hey, limit h goes to 0, f of x plus h minus f of x over h. If the limit exists, we say that's this one, right? That's the derivative at x. So in this notation, which one is variable? Is x variable? No. X is a given number. We just don't know what's it. But praise God, we are His creation. We understand. Yes, it stands for a specific value. And its age changes. Okay, age is the variable. It's not x in this expression. Okay, so here again, here similarly the same. With this expression, age is the only variable. So therefore, we define this. It defines a function of h, right? So you let g of h be that. Okay. So therefore, given that we have f of x is 2x plus 1. How about f of 2x? You can evaluate it. That's, you replace x with 2x, right? It's 4x plus 1. How about f of negative 3x? You say, oh, that's 2. X is negative 3x. So it's negative 6x plus 1. And so on. We play such a game. That's just algebraic, simple algebraic, symbolic game. Okay, so we evaluate g of h, this function, at different points. At which one? At h, you don't need to evaluate, it's solved. At 2h, negative 2h, 3h, negative 3h, 4h, negative 4h, and so on. And therefore, we obtain this group of formulas. Okay, simply, we put this way, g of plus minus kh, you put into this, that's this one, right? And this is this one. Yes. And here in the notation x1, x2, x3. So how about x2? x2 is x1 plus h. x3 is x2 plus h. It's x1 plus it's plus which one here? 2h. If you have x0 there, x1 will be x0 plus h. Now this is x0 plus 2h. This is 3h, and so on. So xk will be x0 plus kh. Okay, we have that kind of simple relation. Okay, so we evaluate this function, okay, with different h. 1h, 2h, 3h, we have this, and we have this group of formulas. Yes, they are so good. Actually, you can have more terms. You can list more terms, but here, for convenience, okay, have for the following contents, they are enough. Okay, we don't need many more terms with each infinite series. Okay, we'll use them to derive formulas for numerical differentiation, and we derive formulas for numerical integration, and later we'll see we'll use it to do other things. Okay, many things we can do can be done through this group formulas like this, and given that the data points are evenly spaced. Okay, we also can use this group formulas like this group, okay, to estimate truncation errors. Okay, we'll see now. How about we'll derive a 2-point finite difference formula for force derivative. Say, hey, f prime at xi, how to find the derivative at xi. That's our purpose. Okay. Now, here, we given this, we have formulas, right? We just pick up 2 here from the group you saw before. Okay, now forced derivative. Yes, that's forced derivative. And okay, when we derive a finite difference formula for derivatives, this is xi plus 1, x sub I plus 2, and so on, x sub I minus 1, x sub I minus 2, and so on, right? Okay. If we derive formulas for this just using points like this, that's forward. Use xi plus 1, xi plus 2, that's forward formula. Formulas. If we use points xi minus 1, xi minus 2, that's backward formulas. Okay, so now we'll see. How about 2-point? The first one, 2-point forward difference formula. That means we will use which thing? We will use forward 2-point. That's 1 point. That's one. That's a 2-point, right? 2-point. Okay, so we'll use xi plus 1. So we don't need to use the first one because it has x sub I minus 1. We just use this one. Okay, we want this formula. And so this is just f of xi plus f prime of xi h. And this term, we cannot assume it's 0. Okay, so that's capital O, this one. Okay. And so from this formula, that's this f of xi plus 1 to this. And now how to find this? From this we find f prime at xi is f of xi plus 1 minus f of xi divided by what? You need to divide by h, right? Divide by h. And big O of which one? H. Because that's h squared divided by 1h. You have 1h left. Yes, that's it. Okay, as I said in that very video I mentioned, it doesn't matter, it's plus or minus, so that's why we always put a plus there. And we don't care is it 2 this or 3 this or 5 this, we don't mind, it's constant. It's part of, you can put that as part of the witness. Okay, so that's a formula. That's a 2-point. That's a 2-point xi plus 1. It uses 2 points xi plus 1 xi. It's forward. And the final difference for formula for what? For the forced derivative at xi with this truncation error. Wonderful. Okay, we derived the formula. At the same time, we know the truncation error of this formula. When you use this difference to what? Approximate the forced derivative at xi. Okay, that's this. Okay, we have derived the fourth one, the 2-point forward finite difference formula for the forced derivative. Now we'll see how about the backward 2-point backward. That means we will use what? We will use backward 2 is this, right? Therefore we use this formula, not that, because it has x by plus 1. We use that formula, and that formula could be written like f of xi minus 1. It's f of xi minus f prime xi h plus big O of h squared. That term. In the remaining terms, when h goes to 0, this term dominates. Okay, so it's this. And from this, we derive the formula. It's, hey, f prime of xi h. It's f of xi minus f of xi minus 1 plus big O of h squared, right? We move this to the left hand side, this to the right hand side, we get this. Both each side divided by h. This divided by h. Yes, we get a formula. That's called the 2 point. Yes, point 1, point 2, 2 point. It's backward finite difference formula for the first derivative. Again, the truncation error here is also given as big O of h. Interesting, right? Okay, now, okay, as this, actually, this formula can be obtained another way. Can you see? The first one, we started the formula, the 2-point forward formula is this: f prime xi is f of xi plus 1 minus f of xi sub I divided by h, right? Plus big O of h. Okay, can you imagine? Now if h is negative h, change h to negative h. Okay, that will be, this term will be f of xi minus 1. H increment, normally x changes from smaller one to larger one, right? It could do in the opposite direction. X could change from larger one to smaller one. Okay, if you go from this point, use a negative increment, that will be xi minus 1 minus f of xi over a negative h. This is still big O of h. And that when you rewrite it is this one, right? Yes, it's, you change h to negative h, you get it, the other formula. Okay, so basically speaking, you can play such a game. If you have, we have derived formulas for, or how many points are used, it doesn't matter. Okay, you change h, if given that you have a forward difference formula, now according to that formula, you let h be negative h, or be replaced with a negative h. You get the corresponding backward difference formula for the same derivative. Okay, that's interesting. So algebra is just wonderful. Here, nothing is new. It's algebra. Okay. Now we can derive another one here, a 2-point central formula. And 2-point central, when we say it's central, is this 2-point central, or how many points central formulas? Okay, it's this xi. If it's central, you have this. Okay, it's the center xi. Okay, 2-point center. Therefore, you cannot use this to xi minus 1 xi. That's not central. And xi plus 1, 2-point. That will be, as you can see, it's this point and this point. And actually, it's a 3-point central formula, but this guy's coefficient later you'll see is 0. Okay, so now that means we'll use both x sub I minus 1 and x sub I plus 1. We use both formula. We want to find a formula for this, and how to do it? You say, oh, I know how to do it. You add each side. Oh, unfortunately, they will cancel out. You get an equation without f prime. And how can you find a formula for f prime? Okay, therefore this part is not addition. Now, how about it? We just say, how about use subtraction? You see, that's f. Okay, we do subtraction. F xi minus 1 minus f xi plus 1 Oh, this cancel out. No f of xi. This you have a negative 2 f prime xi h. This cancels out. Oh, good. And this survives. That's negative 1/3 f trip prime xi h cubic. Okay, our purpose is to find f prime. Therefore, this term we just know it's big O of what? Big O of h cubic. Yes, it's this. In all these terms, that term dominates. Okay, so it's this. And now you can get the formula. Oh, yes, we needed to do what? Divide by negative 2h. As this guy divided by negative 2h. So therefore you have this, and this divided by h, you have h squared there, right? We don't care. 2 divided by 2 divided by 100, 200, who cares? When h goes to infinity. Okay, so constant thing, those constant multiplier, whether it's it's greater than 1 or less than 1, it doesn't matter. It's constant. It's part of, you may believe it's part of the witness for the big O notation relation. Okay, so therefore f prime simplified is 2h f of x sub I plus 1 minus f of x I minus 1 plus big O of h squared. Okay, that's why we call this formula 2-point. This point, that point, 2-point central difference formula. Okay. And of course, if you believe it's this plus 0, oh, actually it is. You say, hey, this is plus 0 f of xi. Yes. In that case, that will be 3-point central difference formula. Okay, so actually it's 2. This point doesn't play a role in the formula. Okay, so, and this formula is better. Yes, because the truncation error is big O of h squared. When h goes to 0, that's way better than this big O of h. Okay, so that's it. So now from this 3 examples, yes, we can use Taylor series expansions to derive formulas. Okay, and next we'll see even more complicated cases. Okay, now a question. Are the formulas valid everywhere? Say, how about this formula? This central difference formula? Yes, sometimes we simply write this way. Okay, we just write this way. We ignore big O of h squared, such a truncation error. We will not write, hey, it's approximate this. We simply write this way. Numerically, when we do numerical computing, don't feel this is ugly. Actually, for pure math people, this desperately is not acceptable. People will say, hey, when h is small, we know this is that. There is such a relation, right? But we still write this way. It's fine. We know. Okay, what we're doing. Okay, so is this formula valid at any point? That's a question. So be very careful. How about this? If this is x0, that's the first point, and now x1, x2, and so on. And this final last point, given that it's xm, this xm minus 1. Now, can we apply this formula to x0? Can we use this to find this one? No way. Because if the index is 0, I is 0, so I minus 0 is negative 1. We do not have such a point. We do have this point. So therefore, it's this value x sub negative 1 is undefined. Okay, so we cannot use refer to that value and use that value for numerical calculation. Okay, so it's not valid for this. Same reason it's not valid for the endpoint, the right endpoint x sub m, because when I is m, you have I plus 1, m plus 1. We do not have such a point, x m plus 1. We do not have it. So therefore, this formula cannot be applied to the first point, to the last point. Okay, that's this. Be always very careful. Finite difference formulas, each one, okay, have their own some constraints. They may not be available at a point. Okay, now same for this, for the 2-point forward formula. For that one, can we apply it to the left endpoint? Yes, you can do it. Can we apply it to the right endpoint? No, this one is not valid, but it's okay to the left endpoint. Okay, and the backward formula. If you choose to use the backward formula, okay, x I minus this. Now, can you use it to the left endpoint? Oh no, you have x I minus 1. You don't have that point, so it's not fine for this, but it's fine for the right endpoint. This time it's fine. Okay, so that's it. So be very careful when we choose a finite difference for formula. We should be careful, yes, if it's valid at a point. Okay. Don't worry if it's, as you can see, for first derivative we have 3 formulas here, right? We can actually we can derive infinitely many formulas theoretically. Okay, so we can derive many. Okay, even from even practically. Okay, so if one doesn't work, we can choose another one. It's valid. Okay, as this. Now, how about still? We'll use more points to find the backward, forward difference formulas for first derivatives. Okay, so how about this? We'll use 2 more formulas. Okay, here. As you can see, our purpose is to, okay, our purpose is to find f prime. This, whatever operations you do about with those formulas, yes, this term should survive. Okay, this term is so important, otherwise it's meaningless. Okay, now forward. X I plus 1, I plus 2. That's forward. 3-point forward formula. That's 2. Okay, derive. And therefore we'll use xi plus 1, xi plus 2. You say, hey, where's xi? Xi is here, so don't worry about xi always. Or actually, if you really want 3 points, you put this here. F of xi equals to what? F of xi. Yes, you use this 3 for forward. This 3 for backward. Okay. Actually, this f of xi we really don't need to worry because we have this in the expansions. Okay. And as you can see, yes, common sense matters in all fields. Politics, in mathematics, physics, yes. or in our daily life, common sense matters. And we should have some common sense. And as you can predict, the more points are used, the better approximation will be obtained, right? This is also if you want to predict the weather for tomorrow. Okay, you use your experience, your data you collected for today, yesterday, and the day before yesterday. And if you even know even more, and that's even better, the more data you collect, and the better approximation prediction you can make. Okay, so here the same. The more points are used, the better approximation could be achieved. Okay, and so we'll see what should we do. And we have a 2. We need to use 3 points. We derive for this one. This one should survive. And what should we do? And as you can see, because even use 2 points, we can derive a formula. Now we use one more point. Therefore, we wish this term to disappear. If we are, of course, we should be brave enough, but reasonably. Okay, we should not expect this be 0, this be 0, this be 0, more things be 0. Of course, if there could be 0, that's best. But we should be practical and reasonable. Okay, we say, hey, how about to make this guy 0? How to make this guy 0? We say, oh, to cancel out this, we use these 2 formulas. Oh my, let's see. To cancel out this times 4, 4, 4, and this will be 2, right? Therefore, do subtraction. You have 4f(xi plus 1 minus f of xi plus 2. And we have a 3f of xi. Yes. And this, we have a 2f prime xi h. How about this term? It's times 4, that's a times 4, that's a 3, 2, right? And so, therefore, it's minus 2 over 3 f triple prime xi h cubical, right? And this, we have such a term, and now, and plus other terms. Okay, in all those terms, this term dominates when h is small, so this term is simply big O of h cubical. Okay, now you change this formula, you will see. How about this formula? This formula will be negative f of xi plus 2 plus 4 of xi plus 1 minus 3 f of xi over 2h. So we have f prime of xi equals to this. Truncation arrow divided by h each side is bigger of h squared. Oh, good. We have finished this. And as you can see, we cannot make this term 0. Yes. So that's it. That's a 3-point forward finite difference formula for f of x prime with this truncation arrow. Yes, it conforms our common sense. The more points are used, the better approximation could be achieved. Yes, that's this. That's a forward 3-point forward formulas. How about can we derive this? Okay, now let me. I'm now using PowerPoint. I cannot. Sounds like it doesn't give me a lot way good way to manipulate my writing, and in OneNote it's better. Okay, maybe later I'll find a way to use OneNote. Okay, now how about backward formula? As you can see, we change h to negative h. With this formula, we'll get what? F prime of xi. This is negative 2h, and this is negative f of xi minus 2. This is 4f of xi minus 1 minus 3 f of xi plus big O of h squared. Wonderful. Okay. We change h to negative h. We have this. Of course, we don't like this formula with a negative, so many negative sign, right? That's positive. That's positive. And this is negative. Yes, that's the 3-point backward formula. This is the 3-point forward difference formula. Okay, interesting, right? Okay, now we still will use more points to derive derive finite difference formulas for students. Now, how about use 4-point? It's central. Normally, it should be 5-point central difference formula, but when we say this is 4-point, that's because of the final result like this. Okay, and no f of x doesn't appear here, and you just imagine you have, as I said, 0 f of x. Yes, it plays no role in the calculation. It's 4-point central formula. Okay, we'll see how to derive. This time, again, the more points are used. Therefore, we wish more terms to eliminate. And this term should always survive. And therefore, we wish this to disappear, this to disappear. We even wish this guy to disappear if possible. If you use computer code, it doesn't matter, you try. If it doesn't work now, you say, hey, if this I cannot make it 0, therefore at least we can make this to 0, right? And if this you cannot, then you just try an error. That's research. It's also a way. Okay, try an error. Now it turns out we can make all this error. Okay, by what? This time, because more equations are used, it's more complicated, and therefore we let the computer to help us. Okay, given that we multiply the fourth equation each side with a, capital A, therefore that's a, this a, to a. Okay. And the second one equation, each side is multiplied by b. You have b, 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 b. Okay. The third one c. Each multiply each side c, 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 c. And then the third one, last one is multiplied by d. Yes, you just do this d, 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 d. Okay, now we add all this. A, B, C, D are constants to be determined by computers. Okay. And so you add the left-hand side, the left-hand side, the right-hand side, okay, separately, respectively. Okay, now we wish, yes, we will have this left-hand side is this right-hand side. This term we don't know will it be eliminated or not. It doesn't matter. The coefficient for f of xi is k. Actually, it's a plus b plus c plus d, right? That's k here. And this term must survive f prime. So we will have this. How about its coefficient? We don't know. And then we know it's negative 2a minus b plus c plus 2d. That's m. Okay, that's m. And we want this term to disappear. So therefore, you have a 2a plus 1 half b plus 1 half c plus 2d is 0. We want it to be eliminated. Okay. Now this term, we also want it to be disappear. Negative this a 4 over 3a minus this. Okay, plus this, so that's the second equation, fourth equation. Now this one, we want it to disappear also. Yes, you set up the equation. Okay, actually, if you set up an equation, you should know how many terms should be 0, could be eliminated. Why? Usually you have n equations. We want to have n. If we have n unknowns, we want to have n equations, right? Okay. So here, you see how many equations we could set up? How many unknowns? We have a, b, c, d. We have 4 unknowns. Therefore, we need 4 equations. Okay. And this one, this one to disappear, set up 1 equation. This one also is set up the equation. This one also, you already have 3. Could we set up the other one 0? No. We set up 3 equations. We will see what will happen. Because that one, if you try, you'll see there is no solution. You let computer do it. Oh, okay. Oh, now you have 3 equations in 4 unknowns. It's a linear system anyway. Any linear system has 3 possibilities. There is no solution at all. There is exactly 1 solution. There are infinitely many solutions. And of course, we wish we could have a solution here. Okay, so as you can see, if A, B, C, D, those coefficients works, how about 2A, 2B, 2C, 2D? Each side is multiplied, it still works. It's given A, B, C, D work. Okay, therefore this works times 3. Yeah, yes, it works. Times any constant, non-zero constant, it works. So actually, if ABCD works, that's a solution. And KA, KB, KC, KD, they are also a solution. So those solutions, they are parallel. Okay, so therefore, one choice is we have 3 equations, we wish we have 4. Therefore, we let A be 1, we'll see. We let computer try. Because the solutions are parallel, so you can let A be 1, or let B be 1, or let A be 2, A be 3. You can try. And now I just let A be 1. We'll try. Therefore, you have 4 equations in 4 unknowns, A, B, C, D. Now, this is the code for in Mathematica. Okay, you just solve it. Mathematics just gives us the answer. A is 1. This is 1, A is 1, B is -8, C is 8, and D is -1. Yes, so that's why we have this. And remember, this K is A plus B plus is that, so this K is 1 plus -8 plus 8 minus 1 is 0. So we don't have that f prime, f of xi there. And m is the coefficient of f prime is -2a minus b, -2a minus b plus c plus 2d. Yes, you calculate. Therefore, m is 12. You calculate. Yes. So therefore, we have such a formula, and this term cannot eliminate, so it's divided by h, therefore it's big O of h to the 4th. Oh, okay, it's wonderful. Okay, and okay, And this ability, as you can see, this shows the ability of mathematical in symbolic computing. Okay, now we'll see. Yes, we have done some examples about developing or deriving finite difference formulas for first derivatives. How about the second derivative, the third derivative, and all of derivative? Yes, it doesn't matter. We can do it through similar process. Okay, now how about just say we'll use this group of formulas, the Taylor series expansions, okay, to derive formulas here for second derivative f dot prime at xi. Okay, 3-point central formula. That means we'll use x 3-point xi minus 1, xi plus 1, right? So xi is the central point. Yes. And we want to find the second derivative. Okay. We want this. Yes, when we derive a formula for the second derivative, f prime should not survive. If you have f prime there, how could you get f dot prime? This guy should eliminate. And obviously, as you can see, how can you get rid of f prime? Yes, with subtraction, with addition or minus plus here, of course. We just add the two. You have f of x I minus 1, f of x I plus 1. You have this 2, f xi. This cancels out. And this is just f dot prime xi h squared. And this term cancels out, and this term survives. That's one interval, f to the fourth order derivative, h to the fourth terms, and that term dominates in all the remaining terms. So it's big O of h squared. Okay, nice. Therefore, the formula, you can tell from this, we know the formula. It's what? F of x I plus 1 minus 2f of x I plus f of x I minus 1 divided by h squared. That's f prime dot prime xi, and divided by h squared. Oh, that's 4 originally, so it's big O of h squared. Okay, that's 4. Okay, that's the formula, and that's the finite difference formula for second derivative. This is it's a 3-point. We have used 3 points. 1, 2, 3. It's a 3-point central formula for the second derivative. Okay, it's so easy to get, right? Oh, we can also derive 5-point. Okay, similar process. We can derive the 5-point central difference formula that will use all those points from, right? We want to cancel out this, and actually, just simply add all the terms. This will cancel out, right? Good. So we just do addition. You can have what? Another formula. That's f of xi minus 2 minus 1 plus 1 plus 2. And how many? You have 4 f of xi, and this out, and this survives, and we can see how many. That's 1, that's 4, that's 5, f dot prime xi h squared. This term cancel out. No, this term. How about that term? This term will survive. It's big O of h big O of h to the fourth. Okay. So what can I cancel out? So it survives. And this again, let me see, yes, this survives. This time they cannot cancel out, so it survives. So you can derive a formula, minus f of xi for this, minus 4 this, you remove this to the other term, and divide by 5h squared. That's h squared. Ugly. 3-point formula we can get. Here's a 3-point essential formula. We have big O of h squared, and this 5-point essential difference formula we also just get this one. this this formula sounds like it's good. We may be able to derive more, and we wish if we use more, you set up a more complicated one, like what do you see? We use computer, I use mathematical code. You want to cancel out to find A, B, C here, A, B, C, D, A, B, C, D. Each side is multiplied by A, B, C, D with each equation respectively. Okay, and if we want this must disappear. We want this, and even this to disappear. Okay, and now you have big O of h to the 6th. Okay, and that formula is more complicated than this guy. Okay, and if there is a solution, therefore it will be big O of h to the 4th. That should be better than that one. Okay, that's this. Okay, we have finished the first one. Second one, and a 3-point forward difference formula. I don't believe we need it. It's already many minutes. I cannot do all. Okay, we just stop here. Okay. Right. Okay, that's the finite sum. That's not all. That's just a very small number of the finite difference formulas for the first derivative and the second derivative. Okay, here. Okay. If you look at the formulas, you will figure out you can easily discover some wonderful properties. What? The first one, say the sum of the coefficients in the numerator is always 0. You verify each one. Say this is 1 minus 1 is 0, right? And negative 3 plus 4 minus 1, yes, it's 0. 1 minus 1 is 0, yes. 1 minus 4 plus 3 is 0, yes. Each one you verify is 0. And that's a conjecture. Can you prove it? For central difference formulas, the proof argument should be quite simple. For forward, backward, and if you just do one, say forward, and it's more complicated. Okay. And therefore, using this, you check on your book. There is such a formula, 7-point central difference formula for the fourth derivative. Wow, it doesn't satisfy this one. Okay, so therefore, when I saw this, I believed it was incorrect. Therefore, now I calculated. I found it's this. Okay, I found this one. It's this, the correct one. So, and based on the very formula, it's hard to tell which coefficient is wrong. That's tough. Okay. If you have one coefficient wrong, maybe you can correct it just by that understanding or conjecture. And also we should know in the formula the points, we want to find the derivative at xi. So the points, we use different points. And if you count the coefficient of each, the coefficient of f at a point as weight. Okay, we should have a common sense. A node closer to xi should have larger weight. This you don't count -3, count 3. Okay, absolute value. Okay, say xi usually is 2, but here xi is closer. It's closest to itself, right? It's 0 distance to itself, and that's exception. No. Okay, you see this 4. This is away from. It's closer than this point to xi, and with each formula you can count this way. Okay. Okay. You may make other conjecture, and one is this: the central difference formulas normally they have better accuracy. Yes. Yes, for finite difference formulas, interesting. There are finite difference formula calculators, the finite difference calculator, coefficient calculators, and so on. And I started a project in that year, 2 years ago, in the winter, and okay, it's open source. You can find it here. First, use Julia, that language, implement the code, and then I just ported it to Python. Okay, you can find it there here. And this is a wonderful, it's a comprehensive toolkit for generating finite difference formulas, and it's quite general, and okay, it just works Taylor series expansions, and so it's just a wonderful tool. You can generate points, difference formulas. So say, hey, xi, use xi plus 1, xi plus 2, plus 3, and so on, and the next backward anyway, and you use consecutive points. Actually, with this toolkit, you can say, hey, I don't mind, I use this point, and some points way far away from xi, use some points. Okay, the points you use, they don't have to be consecutive. And you can use points from both sides of xi. From the left hand side, use some points. From the right hand side, use some other number of points. Okay, they don't have to be really just center. You have so infinite and many possibilities there. You can see it will generate formulas very quickly. You can use the toolkit to generate exact formulas. Okay, with the truncation error. And you can generate formulas for a derivative using 100 or 1000 points, as many as you wish. But that's theoretically, that's for fun, that's a game. Okay, actually in practice you don't need it. As I said in the previous video, we don't use too many points, too many terms. If you use the runoff errors, I mean, the accumulated runoff errors could be a big problem. On the other hand, and the computing power, more computing time is needed. Okay, and with the project, you just, if you are interested, you just you start Julia, you install it. You start Python 3, you install it. And how to use it? Yes, it's like this. This shows how to use it. And you use those points, or anyway, you just type, and it will give you the formula, and it will give you truncation error, and it will give you even a function, say in Julia or in Python, for the very derivative using the very given points. and then later you can copy paste to your code, you use it. Okay, and that's it. Today's topic. Okay, and anyway, we have started, in summary, we have started how to use Taylor series expansions to derive formulas, finite difference formulas, okay, for derivatives, and with truncation arrows. Okay, and by the way, could we use Newton's interpolating polynomial, Lagrange interpolating polynomials to derive formulas, the finite difference formulas? Yes, the answer is yes. And some say if you use Lagrange interpolating polynomials, possibly it's even easier than using Taylor series expansions. But unfortunately, it cannot give us which one? The truncation arrow. Taylor series expansions or Taylor series is just the only tool we can use. I believe the only tool we can use to give a theoretical analysis of the truncation arrow. Okay. So if you use Lagrange interpolating polynomial to derive a formula, that's good. Then you use that formula as guidance, and now you manipulate with Taylor series expansions again, and okay, you can get the truncation arrow. So in module 5, you have some read items. You read it. Okay, please read. Okay, this talk is simply for this module, and actually in the following chapters we will see applications. We'll see more Taylor series applications later. Okay, thank you for watching.